Hope you're ready for the next episode. Hey, hey,
All right, guys. Hey, welcome. You made it. Week 1, Lecture 1, ESYST-101. Let's get it started. We've got a lot to talk about this first chapter, but it's really laying the foundation and the groundwork for understanding why electricity behaves the way it does. So, I don't need to ask. I know you guys are rock stars. You all read Chapter 1 front and back several times over. So, this is just going to be a glossing over of stuff you already know. So, let's get into it. All right, we're going to talk about brief history of electrical discovery, some of the major players therein, the atomic structure, which is extremely important to know, atomic forces, what's causing these atomic reactions to happen, and then we're going to talk about static electricity. All right, so a brief history. Let's go back, way back. We're talking Greece, 600 BC. Ancient philosopher thinker Thales noticed that when he would take amber and wool and would rub them together by some mystical power, it would cause little pieces of parchment to just float up towards the amber. And he wasn't sure exactly what was happening, but he knew there was some kind of force that was pervasive in almost all natural materials. And he wasn't too far off. So let's fast forward 2,200 years, and we've got early experimenters still trying to solve this problem. And they recognized that unlike items or materials would attract towards each other, while like items for some reason would repel. So there was a very prominent thinker during that time. His name was Charles Francois Dufay, and he thought that there were two different types of electricities that were going on. These two different electrical forces, and he named them. He named them vitreous and resinous. And his hypothesis, his speculation was that there was this invisible fluid being exchanged between these physical items, and he wasn't quite sure what it was, but he conceptualized this hypothetical fluid transfer, and he called it a charge after the parlance of the day with charging wells, the way water behaves. And going with the water theme when we talk about electricity is not far off at all. And you'll see as we get further into chapter 1 exactly why this is. So let's bring it a little more modern day. We're talking about now Benjamin Franklin, one of the huge thinkers of the time, huge scientific heavy hitter, came up with numerous concepts about the electrical forces. But he still kept going with the parlance of the time, that there was some kind of invisible fluid transfer that was happening when you would take two different unlike items. He worked specifically with wax and coarse wool, and he noticed when he rubbed them together, that attraction would still happen. And his thoughts were that somehow, some way, that invisible fluid was being pulled from one item to the other, and that attraction that we saw between these two items was actually kind of an equilibrium of sorts, that somehow the fluid was trying to regain balance between its original element and where it was displaced to. He also thought, rightfully so, that materials also always fall into one of two opposing categories, and depending on those categories, when they interacted with each other via through mechanical force, heat, or chemical reaction, that they would have one or two outcomes. They'd either repel away from each other or they would be drawn towards each other. Also correct. So we know that we can solve the mystery of invisible fluid. And I'm so glad to, because I don't even want to talk about or say the words invisible fluid again. So we know this has something to do with the atom. Atom, by definition, means indivisible, and it's a uniquely amazing structure that essentially makes up all things, not to be too dramatic, but everything in the universe due to a unique arrangement of three different fundamental particles. And we're going to get into those right now. But I just want you to think about that for a second. Everything that you can ever imagine that you've come across, every physical reaction, is made up of a simple conceptual structure that only has three parts to it. And we're not going to get into like subatomic particles like meson, quarks, gluons, fermions. That's stuff for another class. Don't get me wrong, we can geek out about it all day, but we're talking about specifically protons, neutrons, and electrons that encompass the structure of the atom. So let's dig into to some notes real quick, and let's try to conceptualize this so we can get an understanding of what this looks like. So right now what we're doing is we are looking at an atom. And if you look at this at first glance, it almost looks like it represents a pictograph of a solar system. And the parallels to that analogy are uncanny. Let's take a look at what we got here. We've got this unique looking mass in the center. We've got these crazy orbits going on here, much like planets or moons, something to that effect. And it's almost completely synonymous with what we see in solar bodies. How so? All right, so let's look at this mass right here. We call this the nucleus. And in this tightly clustered portion at the very center of the atom, we see two particles that are always found. These are our protons and our neutrons. Orbiting this nucleus, we see electrons. Now at the center of the atom, our protons have a very unique role. You see, these guys identify the element of the atom. It's merely by changing the number on why we have different materials or different elements. Now this has been like the big goal of alchemists since the beginning of time, right? Take lead or something uninteresting or unvaluable and make it extremely valuable by changing the number of protons and transmuting it to gold. And it's very difficult, if not impossible, to do that on the atomic structure without destroying the atom. But we'll talk about that in a moment. So we've got our protons and our neutrons, and these guys are clustered very tightly, bound in the nucleus in the center. And they have, we talked about the different charges, the different fundamental pulls and repulsions in materials. And the protons have a positive charge. The neutrons, their charge is inconsequential. And then we have our electrons. And these guys have a negative charge. And the electrons go whizzing around in orbits that we like to call shells. Now, if you want to do some comparison between the mass of a proton and electron, they couldn't be more vast. Think of this as like a proton being a large cathedral, this massive building. And if you were to compare the mass of an electron to that, it would be like a fly sitting on a windowsill. That's the type of characteristic scalar differences between these two fundamental components here. Now, when we're talking about electricity, what we're actually talking about specifically is the movement of electrons from one atom to another. So as these protons and neutrons are tightly bounded and they make up essentially the identity of the atom, the electrons are free to move. But I say that with a caveat, because there's some natural laws and principles that indicate not only how many electrons can occupy an orbit or a shell, or how easily they can be liberated to move from one atom to another atom. Now typically, atoms are neutral, right? They're balanced. For every proton that we have thrown in the mix, we should have an equal number of electrons. But this rule gets a little fuzzy when we start to talk about these energy levels, these shells that the electrons occupy. There's a universal phenomena that dictates how many electrons can orbit the energy level of an atom. And we call this the 2n squared rule. 2n squared. And the rationale is pretty simple. We let n take the place of the shells that we're looking at to identify how many electrons can orbit at which energy level in the atom. Sounds a little confusing, so let's break this down. Right now we're looking at lithium. Lithium by default has 3 protons, or 3 positive charges, 3 neutrons, which are inconsequential, and 3 electrons, which are negative. But you'll notice that not all of the electrons are occupying the same orbit. And that's because of this 2n squared rule, where n would be the number of the given shell. This would be the first shell, this would be the second shell, and if we had even more accumulation of electrons, we would put that here in the third shell. And how we identify how many electrons can occupy a given shell is by using this mathematical formula. So let's do a test here. We see that there's 2 electrons in shell number 1, and there's 1 electron in shell number 2. So when looking at shell number 1, let's say 2 times, and we're replacing the letter n with the shell number 1 squared. So we know 1 squared by itself is still 1, times 2 equals 2. This shell right here can occupy a maximum of 2 electrons. Any more than that, it needs to bump out into the next shell. So let's look at shell number 2. 2 n squared, or 2. So using basic math skills, we know 2 squared is 4, and 2 times 4 is 8. It can be occupied by a maximum of 8 electrons. And we can take it one more step further, and let's look at a third shell. So let's imagine there's another ring over here with electrons zipping around it, and that would be 2 third shell squared. 3 times 3 is 9, times 2 is 18. A maximum of 18 electrons zipping around this third shell. And that is the 2n squared rule. But there's something unique about the highest occupied shell of an atom. We have a particular name for this. We call it the valence shell. The valence shell is the highest occupied orbit of an atom by electrons. In this given example, because we have 3 electrons in our lithium atom, this shell, shell number 2, would be our valence shell. So looking at our atom here, we see that there's 1 loose electron zipping around in the second shell. But another way of thinking about this is that there are actually 7 additional spaces that could be occupied, but aren't. And what these represent is opportunities for other electrons to, either by chemical reaction, mechanical reaction, some kind of physical interaction with other atoms, for electrons to temporarily take up residence in this atom, or to use this atom as a medium to push electrons through a path. And it's these gaps here, these potential homes for the electrons, that allow some materials to conduct or be mediums for the movement of electrons or electricity better than others. Now, before we sum up, I want to talk about one quick principle that I know you guys are scratching your head about because you're so astute, and I know you're thinking, okay, I see multiple protons, and if we remember, our proton friends have a positive charge, and they're right next to each other. in this nucleus. They're right here. And we already had the conversation about like charges are repulsive towards one another, while unlike charges are attractive. So what keeps these protons so tightly bound against each other and keeps the atom from literally splitting apart? Within the nucleus, we have this principle called the strong nuclear force. It is a remarkably strong feature of the nucleus that keeps these like particles bound closely together along with the inconsequential neutrons. Now, the strong nuclear force has diminishing returns. It gets exponentially weaker the further from the nucleus of the atom you go. And that's why the rules for the strong nuclear force don't necessarily play well with the concept of the electrons. Because what we can't see by looking at this diagram here, if we were to zoom in and take a look at any one protein and it filled up the entirety of your screen, the nearest electron would be anywhere between 11 and 17 miles away minimum. This is the kind of scale and scope of the atomic structure that is coming into play when we start to talk about these forces. It's really incredible, right? All right, so let's sum up. An atom made of fundamental particles, three of them protons, neutrons, and electrons. Our proton buddies are positive, our electrons are negative, and our neutrons inconsequential. We'll just say that they don't have any charge, or they're neutral. Makes sense. Protons and neutrons live tightly together in the nucleus, and the electrons orbit much like planets or moons in shells around the atom. The outermost shell being known as the valence shell. Moving on, it's the number of protons that indicates the element. By changing the number of the protons, even though the components are identical, that's what gives us different elements and therefore different materials. Protons and electrons usually balance within an atom, but we have names for these edge cases, and we'll talk about that shortly. Protons and neutrons are extremely difficult to dislodge due to the strong nuclear force. Electrons can move freely. They do move around the atom in orbits, but they can leave the atom freely and go on a journey through an entire circuit of atomic structures if there is enough incentive to do so. And we know that if we want to figure out how many electrons can exist in a shell, there's a fairly universal formula that we can use, the 2n squared, n being the number of the shell in question. Now, where we said the number of protons indicates the element, gives the atom its identity, the neutrons can be variable, although we have some very interesting reactions. When a neutron leaves an atom or there's an imbalance from its typical format, it becomes highly radioactive, and we call this structure now an isotope. We also said that electrons are free to come and go more easily depending on the type of material. And by default, atoms have a net neutral electrical charge. The positive protons and the negative electrons balance each other out. They live in harmony. But when they don't balance out, that's when we get ionic atoms, or ions. If an electron is dislodged, so we're no longer balanced, we're losing one of our negative elements, then we call the atom a positive ion. And it makes sense, right? There's more protons, so if you're looking at the scale between protons and electrons, the protons are heavier. There's more of them than there are electrons. They no longer cancel each other out. Although, if an atom gets overloaded with electrons, then there are more negative elements in the scale than there are positive elements. So we call this a negative ion. Alright, so in summary, most atoms are balanced. Equal number of protons to electrons, the net charge is neutral. If we lose an electron, the scales tip. There's more positive components than there are negative components, so we call that a positive ion. If we gain more electrons than we typically see in the atom, then it becomes a negative ion because the net charge of the atom is now negative. More electrons, more negative, more protons, more positive.